So far, we've only looked at series that have positive terms, and we want to kind of expand that out to look at alternating series. Now, alternating series are series that include a factor such as negative 1 to the k plus 1 or negative 1 to the k, and those would have a pattern of positive, negative, positive, negative, positive, negative. And so when you put it in a series, so for example, down here we have the alternating harmonic series, which is positive, then negative, then positive, then negative, and so on. Right? That's an alternating, in this case, harmonic series, because the regular harmonic series is 1 over k. And this is the alternating term, negative 1 to the k plus 1 over k. So it's essentially 1 over k, negative 1 over k, 1 over k, negative 1 over k. Now we know that the harmonic series, we've proved several times over, is a divergent series. Divergent meaning when you add up all the terms, it's heading to infinity. But we want to see what will happen if we alternate the signs. If we make it go positive, then negative, then negative like this. All right, so let's see what happens. So let's find S sub 1, the first partial sum. Well, the first partial sum would be 1, so that's easy enough. S sub 2 would be 1 take away a half, which would be a half, or 0.5. Then the third partial sum, S3, would be 1 take away a half plus a third. And that would be 5/6, right? Because 2 and 3 both go into 6, which is 0.83 repeating. And then we could keep going like this. So I'll put S4 up here. That would be 1 take away a half plus a third take away a fourth, which is 7/12. I just find that with decimals. Or if you like as a decimal, 0.583 repeating. S5 is 1 minus a half plus a third minus a fourth plus a fifth, which is 47/60. Again, just using decimals. S6 would be 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, which would be 37/60, which is 0.616 repeating. And we would keep going like that forever and ever and ever. Let me show you how to find these values in Desmos, and then we can also look at the graph. So in Desmos, I define my function to be negative 1 to the x plus 1 over x. I'm using x there as a variable instead of k, obviously. And then I made a table with x1, and then I have it find f of x1. So these are the sequence values. You can see them right here in purple. They're what the sequence of these values would make. So 1, negative half, 0.33, negative 0.25, and so on, right? So that would be 1, negative a half, a third, negative a fourth, 1/5, negative 1/6, and so on. Then I want the partial sums. Well, the partial sums, the way to do that is to add a column to the table. And you said that you want a sum that starts at 1 and goes to x1, right, because you want it to stop at whatever this value is, of f of n, right, because n is your new variable now for this sum. And you can see that the first values here are exactly what we said they were from doing it by hand, 1, a half, right, and so on. So I can get the decimals out of decimal pretty easily. So I don't really need to see the purple. The purple is the sequence itself, and then what I want to see is the partial sums, and then I want to kind of see what's happening. So you can see the alternating series is going up and down and up and down and up and down. Oh, sorry, the series. There you go. There's the sequence going up and down across positive, negative, and so on. And then when I take the sum, everything's positive because I'm adding, right? And the negatives aren't outweighing the positives. But you can see that it's approaching a value. And I can see it in the table as well. So I got this number from putting in a million in here and kind of seeing where the limit is. So 0.693, because we don't particularly have a way to be able to come up with it. Well, we do, but we're not going to worry about it right this second. So you can see that those partial sums are approaching that blue line. And that's equivalent to the graph that you're looking at here on the paper, right? Oh, and we can see S sub 7. We can just see it with Desmos. S7 was 0.7595. As a matter of fact, we can see a whole bunch of them. So if you set up Desmos like this, then it will be beautiful for you, right? It will be able to find the partial sums for you. We've done that once before, and it's very handy. All right, so what do we notice? We notice that even though they're alternating, they're approaching a particular value. So in here, that line is y is about 0.693, and we can see that the series, the sequence of partial sums, so the partial sums, i.e. the series is approaching that line, that value, right? So as n goes to infinity, that series is converging on a value. So a couple things, right? As n goes to infinity, the partial sums are approaching 0.693. This means that the alternating harmonic which is, it could be -1 to the k or -1 to the k plus 1. It actually, I mean, it matters, but not insofar for the converging part. It converges. And we're getting a guess of what it converges to, which is about 0.693 and some change. So this is fascinating. This means that we can have series that diverge when all of the terms are positive, but that converge when it alternates. Interesting. So that's going to yield to us a totally different kind of test, a test that is just for these types of series, called the alternating series test. This will be a test that we can use on series like this that alternate.